I'd like to talk to you about the contributions that each of the three energy systems make to the amount of energy that's produced for the physical activity. This is called the interplay of energy systems, and it's how they work together to produce the amount of energy required to do a particular activity. If we look closely at the graph that you can see, there are three systems in play. We have the phosphate system, with the anaerobic glycolysis, and the aerobic energy. So they've got alternative names. If we look at the first system, the phosphate energy, that's produced by the phosphate system or the ATP-PC system. That particular energy system produces a lot of energy very, very quickly, but it runs out of creatine phosphate supplies, which deplete over about 10 seconds. The middle energy system that you can see there is the anaerobic glycolysis, which is often called the lactic acid system. You can see that they cross over at the first part of the graph, and that means that the anaerobic glycolysis is producing more energy than the ATP-PC system. So more of the energy that's required is produced using the anaerobic glycolysis than the ATP-PC system. If we keep looking towards the right-hand side of the graph, you can see that aerobic energy then takes over. That means that the aerobic system is producing more of the energy needed to do that activity than the ATP-PC system or the lactic acid system or the phosphate and anaerobic glycolysis. So the percentage that each energy system contributes changes depending on the intensity of the exercise or the time. Okay, so this next slide, that shows us how different energy systems interplay and how they work together and the speed at which they produce things. So we've got the first system on that list, which is the ATP-PC system. And that says that it produces ATP, or it resynthesizes ATP very, 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 very quickly. But it does so on a 1-to-1 sort of ratio. So we use one molecule of CP to produce one molecule of ATP. So that's why it doesn't last very long. Okay, it only lasts for about 10 seconds. And that's because we run out of those PC stores. The next energy system going down is anaerobic glycolysis or lactic acid system. That again produces energy very, very quickly, and that produces ATP at about a 2-to-1 ratio. So 1 molecule of glucose to 2 molecules of ATP, which isn't very much. But the good thing about that is that it produces very, very quickly. The bad thing is that it starts to produce a waste product called lactic acid. And if we continue to use this system predominantly, then this lactic acid builds up. Our body doesn't like lactic acid. When it gets to a certain point, the muscles don't work properly. So we have these other systems. We have the aerobic system. Now the aerobic system can be broken down into two separate parts, aerobic glycolysis and aerobic lipolysis. They break down glycogen and they break down fat in an aerobic way, which means that they use oxygen to do so. Now the bad thing about these is that it's quite slow in the way that it produces ATP, so it's a moderate to very, very slow ratio kind of thing of when it's happening. But they produce lots and lots and lots of ATP. So the aerobic glycolysis, that produces about 38 ATP per molecule of glucose. So that's a hell of a lot more efficient than the anaerobic glycolysis. Aerobic lipolysis, that produces about 100% of about 100 molecules of ATP per molecule of fat. So that's a lot of energy made by that particular system. The thing that controls this is the intensity at which we're working at. So if we're working really, 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 really hard, so we need lots and lots of energy really fast, then our ATP-PC system will be the predominant energy system in the amount of energy that's being produced. If we need it pretty fast, so we're working about 80 to 95% of our max, then it's going to be the anaerobic glycolysis that's a predominant energy system. If we're working less than that, then we're looking at the aerobic glycolysis and the aerobic lipolysis as a way of producing ATP. So that intensity that we're working at, that tells us which energy system is going to be the dominant one. The time at which we've looked at on the other graph, that's to do with the limiting factors of each energy system. So the first one, the ATP-PC system, that's limited by the amount of creatine phosphate that we have. And we only have a very, very small amount of creatine phosphate. The anaerobic glycolysis one is limited by the amount of lactic acid that's produced. Our body can only take a certain amount. Aerobic glycolysis and aerobic lipolysis is simply limited by how much glycogen, how much fat there is available. There's carbon dioxide and water as a waste product. So that's why we breathe out moisture.
Look at the 800 metres semi-final in the last Commonwealth Games. There's Brian. In fact, he was on the inside lane in this instance. Now, on the left of the screen, you'll see Brian's heart rate. Now, just before the race, it's going at about 100 beats per minute. Below that is his speed, and the 3 bar charts at the right, estimate of which energy supply is depending on and how much lactic acid he's producing.
There they go.
The first 200 metres were the fastest part of this race, with everyone running just over 28 kilometres per hour. And you can see pulling ahead there, giving them a strong lead. At this pace, they're all getting about 90% of their energy anaerobically, and that damaging lactic acid starts to build up, so they can't keep up this sort of pace for the full 800. 200 metres, the speed drops and they bunch together, running now at about 26 kilometres per hour. You can see Brian there in 3rd place. What's important now is for him to stop lactic acid building up, so he has to switch over and start using aerobic energy, which means a steadier pace.
But it's Kenya 1 and 2, Scotland, then Botswana, then England, New Zealand.
400 metres and the bell for the last lap. The speed drops further. They're all measuring their pace. They're keeping the lactic acid down so that they can tolerate it shooting up in a fast finish. Brian's using even more aerobic energy and managing to keep his lactic acid levels really pretty steady, which will leave him with a good for the final sprint. By 600 metres, his heart rate's up to 170 and the speed is creeping up again.
He can bid his mate a run from the outside. It's a brave run. And Brian Whittle's put his shoulder down and he goes as well. And that means
28 kilometres per hour, and they switch back to anaerobic energy, and they're all producing huge quantities of lactic acid, which slows some of them right down. But Brian's okay. He keeps going and comes in 3rd.